Right, good morning, everyone. This is our final lecture this week. So next week there'll be quite a work on molecular docking. What we've done this week to this point is we've had a look at constructing molecules. We have seen how to do some calculations on them. Well, before that we've done conformational searches, for example, Marvin's sketch. But we've seen how to save them as Gaussian files, Gaussian input files, and how to edit them so that we can get a decent run going on Gaussian. We also know that we can save it as XYZ and run XTB semi-empirical method on it. Okay. The other thing we did yesterday is we had a look at the different methods that we use, and a method also, you also work with a method, you also work with a basis set as well. So within the level of theory that you're working, you will have a basis set. And of course, the bigger the basis set, the more accurate your result. And of course, it takes longer. So you need to achieve a good balance between what computing resources you have available and the accuracy you want. Okay. So higher accuracy is not always better. If it's going to take too long to finish the project, then there's a problem. Okay, and let's see. So we know that we can use Notepad++ to edit the COM files, and the most important directives you need at the top is the memory and the shared processes. But I do advise you to also do the checkpoint %CHK. So create a checkpoint, particularly if you want to look at properties of molecules. Okay. Just to give you a little bit of an idea of what else you can do in Gaussian. Is there a question? No. Okay. So yes, you can change your theory. You can do semi-empirical work, in which case you don't need a basis set, but you can use a hybrid DFT, in which case you can use a medium basis set or an accurate basis set, for example. So these are things we can do, but these are all optimizations. So you're telling it to optimize the molecule. What if you've already optimized the molecule? What could you do? Well, we've also done frequency. We've got a theoretical IR spectrum from the vibrational analysis that directs Gaussian to perform. But of course, you can also do NMR. So if you've got an optimized molecule, make sure that the molecule is optimized. So it's been run through Gaussian before. You can get an NMR prediction. You could even optimize if you've got if your molecule is close to being a transition state. If you've made the bond, if you've got a very good guess in your transition state geometry, you can optimize to a transition state using Gaussian. So Gaussian is not just stuck to optimizations. There's a lot more that it can do. And this barely even touches the surface of what Gaussian can do. I really recommend that you look online and you'll see hundreds and hundreds and hundreds of different methods. There are more basis sets than just the purple basis sets that I'm talking about. There are different levels of theory. You can put you can have periodic systems. You can work with crystals, for example. So there's a lot more to Gaussian than just this, but we don't have time to go into it all. Hopefully I've sparked your interest, and hopefully while doing the project work that you need to do for this course, I hope that you are thinking at the back of your mind how you can use maybe Gaussian in your own honors research project. And of course, now would be a good time for you to, if you've got a little bit of time on the side, to get some results for your supervisor. Okay. Just another couple of points that you need to know about in Gaussian is that there's this Norton 1 that that are just before all the atom specifications, and that's the charge and multiplicity. Here you see I've got the checkpoint file in, which is correct. The blank lines are important. There must also be a blank line at the end of a file. But of course, if you run Gaussian and you get a problem, just email me. Apologies, yesterday was a bit of a disaster for me. I was working with the NMR, and that took a lot of time. And so I didn't respond to everyone, but please, I will respond. If you have a problem with Gaussian that doesn't run, just drop me an email and say, there's this file. Can you just troubleshoot quickly? And I will give you ideas on where to look for troubleshooting. Okay. So on the cluster, I really recommend, if you don't know where to start and you've got only a few molecules, use B3LYP with 8 processes. If you do know where to start, if you've got lots of molecules, use XTB. But of course, if you do know where to start, you can use a much higher level. It is slow, but it's relatively accurate. But of course, be guided by literature. And of course, we've got 2 Qs there. Just use the appropriate Q that you need. Okay. And so the perhaps a final point that I need to mention is, yes, we've looked at orbitals. You can look at spin densities. You can look at UV vis absorption. So with Prof. Max course, you're going to have a look more with properties. So if you're going into Prof. Max course, make sure you're comfortable with getting Gaussian runs on the go and submitting them to the cluster. But my final point is that when you do that, we did an opt plus freak. When you do an optimization plus a frequency analysis, you get very, very accurate energies out of it. And so what you need to do is use Notepad++ to open that output log file. And it's pages and it's thousands of pages of output, but you have to search through it. If you search through the pages of output, you'll see these lines. If you've done opt and freak, you will see these lines in the log file. Open the log file, scroll through and find it. And what's really nice is you get the sum of electronic and thermal free energies. And this is your G value, your free energy value. And so if you want to compare it to another conformer, if you want to compare it to maybe where reactions happen and there's been a rearrangement of the atoms, this is the value looking for. It's in Hartrees at the moment, but of course you'll be able to convert it to kilocalories or kilojoules per mole, depending on what you need. Okay, so the opt plus freak, it's not obvious after you've run it, but if you open the log file in a text editor, you'll be able to search and find that. Okay, so that's where we are in terms of preparing the ligand. Okay, right. So I'm just going to carry on a little bit and just show you where we are now heading for. Just hang on. Yes. Apologies. Okay. Right. So we should, at this point, have high quality ligands for work. So I just don't want to lose sight of where we're going in our write-up in our project. And in our write-up in our project, what we want is we want small molecules to be combined with a receptor through a process called molecular docking to see whether that small molecule is going to fit perhaps within the active site of that molecule. So we've certainly got high quality small molecules to work with. We've got high quality ligands to work with. So the question is, what do we do with it? Well, of course, we've prepared the ligand for docking. We did that yesterday in the practice section using Autodoc tools. And so we know that we can use Babel. We can use Babel to convert a Gaussian log file to PDB. And then what we can do is within Autodoc tools, once you open Autodoc tools, we can use the little ligand menu to open that PDB. We'll have to change the type to PDB. And then it finds the rotatable bonds, and we save it as a PDBQT file. It's interesting looking at a PDBQT file in Notepad++, because you can see where the branches are and where the rotations are. Okay, so that's quite interesting. And that prepares the ligand for docking, so the docking software knows exactly where it can rotate the ligand to search for conformations for different arrangements of atoms of that ligand. Okay. Right, now what about the receptor? What about the protein that we're going to try and bind to? Okay, for what we would like to do is we need to get a good high quality protein structure, and there are databases you can get them from, and we're going to be using the RCSB to retrieve as proteins. We'll get 5 at least from the RCSB. Okay, now what we will do is we're just going to remove all waters from the system, because when the structures are generated through single crystal X-ray diffraction, waters are present, and those show up in the crystal structure. I don't know whether some of the waters will occupy some of the space that where we want our ligand to work. And so blindly at this point, I will just suggest that we remove all waters. When you get to know your structure a bit more, you might realize that some of the waters are important for binding, and they provide a bridge between ligands and the protein. But then you need to really know your structure very well, and you really need to know every single water that is within the active site and its purpose and where it is. But for now, what I would prefer to do is I'm going to remove all waters from the active site. Right, now what we've got to know, what we need to also know is where is the active site? And knowing the X, Y, and Z coordinates of the active site is good. And how do we do that? Well, often when you get a protein from the RCSB, that crystal structure includes a ligand there. And so we can use the existing co-crystallized ligand that is already in the active site to tell us where the X, Y, and Z coordinates are. Okay. Sometimes there are cofactors that are bound to the system, and often you may want to leave the cofactor there before you try and do molecular docking of your molecule to the system. Okay. So what we've got to do is the problem is we cannot get our molecule into the protein if that co-crystallized ligand remains. And so we've also got to remove that co-crystallized ligand from the active site. Okay. We may need to determine the protonation states of residues. Yes, we will have to do that, because if you get the protonation wrong, then you're not going to get the perhaps possible hydrogen bonding interaction. So protonation is really important, and we'll have to confirm atom types and charges for calculation. Okay. So we're going to get some structures from the RCSB. And so we just go to rcsb.org, and I've told you some structures. We can just search by the codes I've given you, and you'll very easily get to those codes. Of course, you don't have to search by the code. You can search by organism. You can search by enzyme type, for instance. So you're not restricted to those codes, but just for now, there's some codes that I would like us to work with in this course. Okay. I cannot remember if 6WMP is one of them, but it may well be one of them. Okay. Right. So we'll have to download some structures from RCSB. Okay. We don't work with Schrodinger software. In the past, when we have access to a lab, I have preferred to work with the Schrodinger software. And of course, if your supervisor's got access, and most supervisors will have access to the CHPC, we have a national license for Schrodinger. So we can easily work with Schrodinger if necessary. And we can do molecular docking on Schrodinger as well. But of course, Schrodinger allows for a very intelligent preparation of the protein, and you can see it can, you see you've got some control about deletion of water. It just tidies up the protein in terms of the structure of protein, in terms of adding hydrogens and disulfide bonds, etc. So Schrodinger is quite powerful and can be used for this. Okay. Of course, there are other options that we have with Schrodinger. In Schrodinger, if you don't know where the active site is, you can ask it to search for sites on the protein to search for. We're not going to do site searches in ours. We're lucky in that all structures that I've given you come with a co-crystallized ligand that we're going to have to remove. But the nice thing about that is that with that co-crystallized ligand, we'll be able to know, it tells us the exact X, Y, and Z coordinates of the active site. So we can easily know where the active site is. But if you've got a protein that has no co-crystallized ligand, and you don't know where to bind your molecule to Schrodinger, we can do a site search for it. Okay. So how do we work with proteins in AutoDock tool? So what you've got in AutoDock tools, remember yesterday we were looking at the ligand alone. When you work with a ligand, you're going to work with this lower set of menus, and you'll go into the ligand menu to start off with. But for the protein, you can use the top menu. So you can go File, Open, and you'll be open the PDB. So remember that for molecular docking, you want a protein and a ligand together, which means that you need to have two files open when you do the docking. So how do we separate them and how do we work with them? Well, it's quite easy because a lot of the time it tells you if you've got two things open, you can choose which one to work with in which context. But my recommendation is use this ligand menu when you want to work with a ligand, and use the file menu when you want to work with the protein. So file open here will open the protein, ligand open will open the ligand. So you'll have the protein from the top and the ligand from the bottom. But of course, how do we delete waters? Well, once we've opened the protein with file open, we can go edit, delete waters. So from the edit menu, you can delete the waters. Okay, right. So how do we delete perhaps unwanted systems there? So some of the proteins that you're going to work with have dimethyl sulfoxide with them, and those are far from the active site. They're not really involved in anything, but I recommend that we just remove them as well, like we remove water. You will be able to scroll through on the left-hand side, the hierarchy, all the residues of a protein. If you go right to the bottom, you'll see these DMSs, and you can get rid of them. You can select them by making them yellow, and then you can go edit, delete selected atoms. Okay, right. And of course, what we can do is we can also find, you'll notice that when you, if there is a co-crystallized ligand within AutoDock tools, you'll see you've got your amino acid residues going through. And if you scroll right to the bottom, you'll find something that looks really strange, it's odd. And that may well be the co-crystallized ligand. In this case, it is. And it's nice to save it as a reference. What we're going to do, what our first task is, and the reason I've got you to draw those 5 ligands, is we're going to try redocking. So we're going to try and take the molecule that's co-crystallized, and we're going to use the software to put it back in. And we're going to say, well, hang on, Does it reproduce the pose? Does it look exactly the same as it did from the crystal structure? Does our modeling reproduce the experimental data? Okay, so we need to see that. So this is our reference. This is the experimental pose, and maybe you can just see it at that angle there. If we take it out and take our drawn structure, which is exactly the same molecule, and redock it, does the docking software get it to exactly this pose again? That's very important in terms of validating what you do. Just like maybe when you do synthetic work, you've got NMR and you've got other tools, you have to check that what you're doing produces what you expect. Same here. If you want to do docking, first thing I recommend you do is you redock a known crystal structure ligand. You take it out and use molecular docking software to put it back. And if the software puts it back correctly, then the docking, you've validated your docking procedure. If the ligand does not go to the active site, or if it ends up with an incorrect pose, then there's a problem with your docking. And how can you trust with your own molecules, if you create new ones, how can you trust when the software says this is an amazing molecule? You've got to validate your docking procedure first. And the way we do it is through redocking, where we know what the pose should be for the ligand. And that's what we're going to start with. But of course, once you have set up your protein, you can, once you've saved that co-crystallized ligand, you can delete that ligand, the co-crystallized ligand. Otherwise, it's occupying the active site. We don't want it to remain there. So we don't want it to carry on occupying the active site. We've got to remove it from, so we delete it. So we're ending up with an apoprotein with nothing in the active site, so that when we do the docking, there's nothing stopping our molecule from going into the active site. Okay, and so we'll be able to delete. Like we deleted dimethyl sulfoxide, we're also going to be able to delete the co-crystallized ligand from it. And then we'll be able to save that PDB as an apo structure ready for docking. Okay. How do you determine the active site? Well, if you save your co-crystallized ligand in a file, of course, when you look at the file, when you open the file, you'll see all the atoms of a co-crystallized ligand, the oxygens, the nitrogens, the carbons, etc., in that co-crystallized ligand. And of course, near it, you will see the X, Y, and Z coordinates. So these first three numbers are the X, Y, and Z coordinates. So that's quite nice. So for instance, in this case, I've saved that co-crystallized, I selected it, and I did a file save of that. And we'll go to Notepad++ and have a look at that file with just the co-crystallized ligand in it. And I can see all the atoms, but I can see X, Y, Z coordinates as well with it. And that can help you to estimate where the center is. And so you could do a center of mass, for instance, or as long as you make the search site large enough, you can estimate, and you can say, well, hang on, the X extent of a ligand, the minimum X extent is about 20, and the maximum X extent is about 26. So the middle X extent is probably about 23. That's between 20 and 26. So I can say the middle of the active site in terms of X is about 23. If we have a look at the Y, the middle of that, this is very rough and ready, but it will work if your extents are fine. It goes between 10 and 20, so I'll maybe choose 15 as between 10 and 20, and this one goes, I suppose, between about 3 and about 6, so 4.5 is going to be a good choice for the center, for the Y center. Okay, so there's X, Y, and Z coordinates. We just need to know roughly where the active site is. Okay, if you're an angstrom out, it's not going to make a problem. We're going to use a search area of about 20 angstroms in our search. So you can see there's going to be a little bit of leeway. So if you're an angstrom or two out, it's still going to make the active site within the search area. And so the software will still place the ligand within the active site. It's not going to be a crisis. However, if you want to be thorough about things, you could maybe look for a center of mass, or you could know a little bit more about your protein in terms of the active site and the active site residues, and you could try and find XYZ coordinates that are particularly around those active site residues. But ultimately, whatever you do, you need to validate your docking procedure, because if these numbers are wrong, you are never going to reproduce the pose with the active site. These numbers are wrong. You might find that the ligand tries to dock in empty space far away from the protein, or it tries to dock in a totally different region of the protein altogether. So you have to be very careful. You have to be very careful in that you always validate your docking procedure. Check that the parameters you work, the active site center that you use, does actually work before you work it on one of your own ligands. So from your own research, just validate, always validate the docking procedure. Okay. I think what I'm going to do is leave it at this point. So what we would like to try and do is we would like to try and prepare proteins in the practice session. Okay, so can we meet in about 12 minutes time at 22 for the practice session? Are there any queries, any questions? Okay, if there are no questions, then let's meet in, I'll meet you in 12 minutes for just we'll be able to get some proteins on the go. Okay.